Hello everyone, this is Mustafa here solving soil mechanics problems for civil engineering students. In this video I'm talking consolidation and we have here question number 10. You can refer to my other videos for more problems. This problem is a bit advanced, but I'm sure you will find it very interesting. What we are given here is a soil profile here that's 4 meters of clay, and we have here impermeable rock. The site will be loaded with surcharge on the top here, and we are given piezometer data at point A. So I have 2 points here, point A and point B. We are given piezometer data. I will explain what we are given here. So before applying any surcharge on top of the ground surface, a piezometer is inserted here. And remember, a piezometer is something that can measure pore water pressure, basically. So before anything, the measurement gave 10 kPa at this point, and then there was a surcharge. The surcharge, when it was placed immediately here, so what happened is the piezometer reading gave 120 kPa. After 100 days after loading of the surcharge that will come on the top here, so the reading of the piezometer dropped back from 120 kPa to 55 kPa. So this is the data we are given in this problem. What's required? Required coefficient of consolidation based on the piezometer data at point A, and we are required to determine the effective stress at a point B here, which is 3 meters below the clay surface, and we are also required to determine the time to 90% consolidation of the overall clay layer due to the surcharge that made these changes in the piezometer reading. Solution strategy: we need to convert the piezometer data to rate of consolidation from these data given at point A, and then using the consolidation parameters that we will be able to get from this step to work out the stress increase at point B due to the consolidation. And finally, we need to determine the time from the average degree of consolidation formula for the whole thickness of the clay. Essential knowledge for problems of that nature: first, we need to know how to apply the consolidation equation at a specific point and also on average, because we are given here a specific point A. So the crux of this problem is that there is a difference between applying the degree of consolidation as an average over the whole thickness and applying it for a specific point. And we need to know also the correlation between the degree of consolidation and the excess pore pressure and the effective stress increase. You will hear me talking a lot here about the excess pore pressure. So let me define it here before we move any further. So the excess pore pressure is what the pore water pressure will acquire in excess of the existing, most probably, hydrostatic pressure. Basically, this excess or increase in the pore water pressure is due to external loading. So let us see how we tackle this interesting problem. So again, this is the soil profile, and this yellow volume here is the surcharge load that basically cause these things to change in reading. So a piezometer basically is something that in the past it used basically to be a reel tube that you inserted, or pipe you inserted into the soil, and the water rises in it. It's still being used the same way, but you can also use something electrical here. So in the beginning, before applying any load, so the pressure here gave something equivalent to 10 kPa. Immediately after loading of this surcharge load, this yellow area, so the reading jumped to 120 kPa. But after 100 days, so it receded again to 55 kPa at this particular point. So let us see how we can work out the degree of consolidation from this data at point A. First, we are given that U naught 10 kPa. This is pretty much close to being hydrostatic. That's 10 kPa before application of any surcharge. I am here just reiterating this so that we can understand the problem together. And immediately after applying the surcharge, I have 120 kPa. This means that the excess pore pressure immediately after applying the surcharge is the difference between the two readings, because the hydrostatic pressure will always be the reference pressure that the water would like to go back to. It's not zero, it's a value. So I have here 120 kPa from the surcharge minus 10, so that's 110 kPa due to surcharge. This is at time 0. And basically, remember that this would be equivalent to delta sigma that's coming from the external agent here being the surcharge. So now I have a piece of information telling me that the excess pore pressure at time 0 due to this surcharge load is 110 kPa. Now, after 100 days, it's 55 kPa. The same way I can work out the excess pore water pressure at time equals 100 days. So it's 55. Remember, we have a reference pressure here, 10 kPa. So the excess pore pressure is 55 minus 10. That's 45 kPa. Now I have several pieces of information. The excess pore pressure before anything was done is 0. And then the excess pore pressure immediately after the surcharge is 110 kPa. And then the excess pore water pressure 100 days after loading is 45 kPa. Let us see how we can use this information to get the coefficient of consolidation. Remember, we are talking about a specific point that's at point A, not the average behavior of the overall thickness of the clay. This is why I am referring here to the degree of consolidation as UZ, meaning that this is a degree of consolidation at a depth Z, happening here to be point A, which is 1 meter below the clay surface. The definition for the degree of consolidation at any particular depth UZ is 1 minus delta U divided by delta U naught. What is delta U? Delta U is the excess pore water pressure at any time. That's happening here to be 45 kPa. What is delta U naught? This is the excess pore water pressure at time 0 immediately after applying the surcharge load. Here it's 110 kPa. So when you substitute in this equation, it's telling me that at point A, the degree of consolidation is 59.1%. That's 100 days after application of the surcharge load. So this means that now we can use this information to determine the degree of consolidation from this equation, which should be very familiar to you, which link actually the coefficient of consolidation, the time, and the time factor. Also included here is the length of the drainage path. We know that the thickness of the clay is 4 meters, and also HD here is 4 meters. This should be H small, not H capital. So it's 4 meters because this is impermeable rock. So the longest drainage path would be all the way from the bottom here to the surface. That's 4 meters. Time is 100 days. So we need the time factor TV. Unfortunately, we cannot use these values from the table because this table, and also it is given in equations that we will see later, this applies to the average degree of consolidation, not to the specific degree of consolidation at any point as point A we have here. So we cannot use this equation, but we have to use something else. I'll explain and elaborate more on this in the next slide. So basically, this is the equation of consolidation, the differential equation for consolidation that was solved by Terzaghi in the past. And when we apply Fourier solution for U at any point using this equation, we get the general solution for the degree of consolidation at any point, UZ. You don't have to be scared by this equation. It's straightforward. We will see in a minute how we can apply it. So that's basically when we plot this normalized, here it is normalized by delta sigma, and the vertical axis here normalized by the drainage length. So this is the excess pore water pressure. So basically the area here at time 0 would be 1. The average degree of consolidation is the area, shaded area here. This is your average. But at point A, we have something else. We have a degree of consolidation specific to point A. That's 59.1%. Now we need to use this to basically work out the coefficient of consolidation. Remember, this approximate equation is not applicable to point A, like I said before. We cannot use it. Because here, I'm reiterating, because this is very critical, because here, all the information we are given are pertinent basically to point A. So let us now solve this Fourier solution, series solution. Straightforward. M is basically pi by 2 times 2m plus 1. That's times, not equal, times 2m plus 1, and the m equals 0, 1, 2, 3, 4. The rest of the parameters here are known. We have m, just defined it. Z is the depth of the point in hand. That's the depth at this point A. HD is the drainage length. We have it 4 meters. And TV is the thing we are after. So basically, it's a complicated equation. We can solve it using goal-seek in something like Excel. So let us substitute here. M here, M small, is basically 0, 1, 2, 3, 4, 5, etc. You substitute for the other quantities. M is a function of M small, and you get sine MZ divided by HD, etc. So you assume TV, and you get UZ until you match the 59.1% from this summation here. It's very, very straightforward. And this will give you a solution that the time factor for point A has to be 0.108 for the required degree of consolidation at point A, which we calculated as 59.1 here. So now I have basically got the time factor T sub V, which I can use to work out the coefficient of consolidation. Straightforward. TV is 0.108, drainage path 4 square here, and the time is given as 100 days. So now I already got the coefficient of consolidation from all the data, remember, at point A. The rest will be straightforward. So here is the profile. Now I'm required to work out the effective stress at point B after 200 days. So what we are trying to get here is what will be the increase in the effective stress at point B after 200 days. First, we have at point B the in situ stress. That's 3 meters times 20 minus 10. It's green here just to remind you that this is the point or the submerged unit weight. 20 is the unit weight of the clay, and the 10 is the unit weight of water. So I have 30 kPa, that's overburden pressure. Sigma dash V after 200 days is basically the summation of the in situ stress plus any increase in the effective stress that this point B will feel due to the 200-day consolidation. It's exactly like what we did at point A, except that we now have the coefficient of consolidation 0.01729. And I have, again, all the information at point B. Depth being 3 meters. Remember that the drainage path is always constant when you apply the general equation of consolidation at any point within this medium. So it's 4 meters here. Then we can substitute coefficient of consolidation, rearrange. I need to get the time factor at point B. So CV is known now, 0.01729. H drainage is known, time is 200 days because this is what's required here. So I got the time factor at point B, 0.216. All we need to do now is to get the degree of consolidation. Again, I have to use the general equation for the degree of consolidation at any point. Solve using Excel. Again, you assume M, but now you have, remember, we have the time factor. So we can just substitute in all these parameters, and the summation here, obviously for more values than the ones that I'm showing here. And when you solve for this, the degree of consolidation at point B has just been calculated as 0.312. That corresponded to time factor 0.216. We are close to get to the bottom of this. Let us define again the degree of consolidation at a point. It's either 1 minus delta U over delta sigma. Delta U is the excess pore water pressure, and the delta sigma is the total stress due to the external load. Or basically, it's the change in the effective stress, delta sigma dash V, divided by delta sigma. So you need to know that these two equations are equivalent. So I have delta sigma, remember, which is the excess pore water pressure immediately after applying the surcharge. We called it delta U naught. And this came as 110 kPa. We did it before. So I can now say UZ by definition is delta sigma dash V divided by delta sigma. I have the degree of consolidation at point B, just calculated it here as 0.312, substitute. And the delta sigma is 110, so I'm able to get delta sigma dash V because I will come and substitute it here to get the effective stress, which is the thing required in the question. So I can now work out the change in the effective stress at point B due to the surcharge some 200 days after application of the surcharge is 34.2. The rest is straightforward. I just need to add this to the overburden pressure being 30, so 64.8. So the effective stress after 200 days from applying the surcharge at point B, inclusive obviously of the overburden pressure, will be 64.8 kPa. Last bit of this interesting question is time to 90% consolidation for the whole clay layer. Like I said, when you draw the pore water pressure here, this line here, we call it the isochrone. At any time, all these points located on this curve basically have the same excess pore water pressure at any time. So this shaded area, like I said before, give you the average degree of consolidation. So I can basically just apply the general equation that we are familiar with, and we can now use these equations and this table. I have 90% degree of consolidation. You look up this table or you apply this equation. So the time factor corresponding to 90% is 0.848. Then I am in a position to substitute here 0.848. Drainage path is 4. And here I have coefficient degree of consolidation, coefficient of consolidation C sub V. So the time here is 785 days. I am able to use this equation because the question in hand is pertinent to the average performance of the overall thickness of the clay. Hopefully you have enjoyed this very interesting problem, and I'll see you